All right, okay. So let's calcium carbide. Let's solve this question. Calcium carbide reacts with water to produce acetylene, as shown in the imbalanced reaction below. So first we need to balance the reaction, right? One calcium, two carbons, two carbons. So initially here, right, you had the two hydrogens in here, 2 plus 2, 4. So that's why I added these two hydrogens here. That makes 4 hydrogens in both sides. The same for oxygen. So now we have 2 oxygens. And here, there's number 2 here, right? The number outside the parentheses here is multiply everything that is inside. So that it means in this formula, you have 1 calcium, 2 oxygens, and 2 hydrogens. That means the reaction is balanced now. So how many grams of water are required to complete the reaction with 82.4 grams of calcium carbide? Now, okay, so let's start with what's given here. 82.4 grams, right? So the first thing we need to do what? To find the molar mass, right? So know that each 1 mole of calcium carbide we have, so let's go to the periodic table, right? Calcium, 3 here, right? 40. Plus each oxygen is 12. So you have 12 plus 12, sorry, carbon. Each carbon is 12, right? So we have here plus 24 plus each, this is carbon. And each calcium is 40. So the total molar mass here, it is 64 grams per mole. Okay, so here, 64 grams of calcium carbide. So let's find the mole numbers first here. Okay, so 82.4 divided by 64. So 1.287 moles of calcium carbide, right? Now let's convert the moles of calcium carbide to know how many moles of water we need. So you know that so here, right? 1 point, so this is the first step. Now let's go to the second. Take the moles here, 8.2, 1.287 moles calcium carbide. Now let's go to the stoichiometric ratio. For each 1 mole of calcium carbide, you need 2 moles of water. So 2 moles of water for each 1 mole calcium carbide. So times 2, you have what? 2.57 moles of water. But the question is asked for what? How many grams? Now let's convert the moles of water to grams. How to convert from moles to grams? We multiply by the molar mass. So let's multiply by the molar mass of water. That is 18 grams for each mole, right? Okay, so time is 108. Oh, so time is 18. here. 46.3 grams of water. So first thing, convert the grams given to moles, right? First step, take this grams given, convert from grams to moles. That means divided by the molar mass. So from grams to moles, you divide it by the molar mass. After you find the moles of the react that was given information, you convert from moles of what is given to the moles of you want. What you want to know? The amount of water. So here, take 1.287 times 2. Now, you have the moles of water. Convert from moles of water to grams, you multiply by the molar mass of water. That's 18 grams per mole. So the answer is 46.3 grams. So in this reaction here, the combustion of propane in the presence of excess oxygen yields carbon dioxide and water. So have here the combustion of propane. So the reaction is already balanced. In this case here, right? 3 carbons, 8 hydrogen, 4 times 2, 8 hydrogens, and then 5 times 2, 10 oxygens, and 3 times 2, 6, plus 4, 10 oxygens, yeah. So when 2.8 moles of oxygen are consumed in the reaction, so let's calculate the amount of moles of carbon dioxide that will be produced here. So this question is very simple. Actually, you just take the moles given and use the mole ratio, find the moles of you want. So 2.5 moles of oxygen, right? What's the molar ratio between carbon dioxide and oxygen? So 5 moles of O2 and 3 moles of carbon dioxide. So this here is from the reaction, the molar ratio here. Right? Then now just multiply 2.50 times 3 divided by 5, and then you have your answer. Can you see that the moles of oxygen will cancel out with moles of oxygen? So your answer will be here. Moles of carbon dioxide, right? Okay. Now, this is about stoichiometry, right? So this question is very simple. You just had to look to get the amount that was given and multiply by the molar ratio. Sometimes the reaction not balanced. So you always need to check if the reaction is balanced. It's balanced, okay? Now, what's the hybridization of oxygen and water? So let's count here. Let's draw the Lewis dot structure. How many valence electrons we have in the water? Each hydrogen is 1, right? So 2 times 1 plus oxygen, here group 6A, family 6A, so we're going to be 6 valence electrons. So the total 8 valence electrons. Now, when you have first the numbers of valence electrons, let's draw here the symbols. Oxygen and oxygen. Oh, sorry, oxygen and hydrogen. Now let's connect here. Each line here is one bond, and each bond counts as 2 electrons. So oxygen and hydrogen, they are sharing two electrons here. 2 electrons. 2 electrons. Let's count it here. 1, 2, 3, 4. So 8 valence electron minus 4 valence electrons for the bonds, right? So you still need to place 4 electrons in the structure. So let's start with the terminal atoms. But the dedicated here, terminal atoms is hydrogen. In a hydrogen, we have hydrogens will be stable with only 2 electrons. So don't need to make 8 to hydrogen. Hydrogen is happy only with 2 stable, right? But oxygen, let's count oxygen here. 1, 2, 3, 4. Okay, so where do we want to place this extra 4 electrons here? Let's place around the oxygen. So have 2 pairs, 2 lone pairs, and 2 bonded domains here. Now let's count. Well, let's count how many. What's the hybridization here? 1, 2. So 2 bonded domains. 3, 4. So 2 bonded domains and 2 no bonded domains. Like each lone pair, you count it as 1 non-bonding domain. So here, how many you have? 1, 2, 3, 4. So with hybridization here, we will have 4. 1, are seen here, S1 is 1. 1 plus 3, 4, the answer gonna be this one. So if you count the numbers of domains and you find only 3, the answer gonna be what? Would it be sp2? Because 1 plus 2, 3. If you find that it's 5, the answer would be this one. 1 plus 3, 4 plus 1, 5. Okay? So now, question 27 here. Write the complete set of quantum numbers that represent the valence electrons for the following elements here. So that case here, the question is asking for all the valence electrons. Okay, now helium. Okay, helium has only 2 valence electrons anyway, so let's go for helium. Helium, right, has only 2, atomic number is 2. The configuration is 1s2. So you have the 2 electrons here, right? Now let's write the set of quantum numbers. N is the primary quantum number, right? That's going to be the energy level here. So 1. Both electrons are in the first energy level here. And then the secondary quantum number here, right, is the angular momentum, is about which subshell you have. So the subshell will have S, P, D, F, right? If it's S, the L is gonna be 0. If it's P is 1. If it's D is 2, and F 3. Okay, so both electrons, they are in the subshell S, right? So gonna be the L will be 0. Okay, now let's find the MEL and MES for each one. So 1s2, you have only 1 orbital, right? They're gonna be in the 0 here. 1 up, the second down here. So the MEL for both is gonna be 0, but 1 is point up, so plus 1/2, and another is pointed down, so minus 1/2. So you see in here that each electron in the atom will have a different set of quantum numbers. So for this one, right? When one is 1 and one is 2. Both for the energy level, the same subshell, the same orbital, but different spin, right? Now let's go for the magnesium. Magnesium here, right? 12, 12 atomic number is 12. Magnesium here. 1s2, 2s2, 2p6, 3s2. So 2 plus 2, 4, plus 6, 10, then 12. Okay, and then the valence electrons are the one in the highest energy level, the outermost shell. In that case, we're going to be this one here. So let's find the set of quantum number for these 2 electrons here. The first one is what? Energy level. So going to be the first one here. 1, 1, 1. L is the angular momentum. That's about which subshell is we have here. Subshell S. What's the L for S? 0. In that case here is also just the ML, no orbital 0 here. And the same thing gonna happen here, right? One up, the second, and then the node is pointed out here. So now let's see for sodium. Sodium has only one valence electron. So if you wanna see we can find the valence electron for sodium just looking here, right? This is the S block. So 3s1. Right, so sodium is a 3s1. Sodium has only one valence electron, so just need to have to write one set of quantum numbers. So the energy level 3. The subshell is S, that is the angular momentum here, that's gonna be 0. So if the L is 0, MEL also will be 0. In that case, just one electron gonna be pointing up, so plus 1/2. Okay, now let's talk about carbon. So carbon is in the group 4A, right? Family 4A here. So this is the block P. So what's the valence electrons here? Right, so let's find the how many electrons we have here. Carbon is 6 valence electrons, right? So let's write it here. 1s2, 2s2, 2p2. This is for carbon. This one here, right? Carbon. So carbon, you have 4 valence electrons. 2 in the subshell S, another 2 in the subshell P. So I needed to say the electron configuration for both here. So let's talk about the first 2, 2s2. Energy level 2. The L for S is 0, right? So 2 electrons in the subshell S, we'll have just one condition here, right? MEL gonna be 0, and 1 point up, the second point down, so -1/2, and another one's gonna be the same, right? Now let's see about 2p2. The P fits up to 6 electrons, so 2p2 here. they have 3 orbitals, right? And each orbital fits up to 2 electrons. So for P, the MEL will range from -1 to +1. And for P, the L is what? 1. L is 1, so the range is going to be from -1 to +1. For D, the L is 2, right? So the MEL will range from -2 +2, from -2 to +2. So here, 2 electrons, so up and up, right? You first need to draw all electrons up first in the semi-orbitals, and then you're going back to draw, pointing down. Okay, now let's see this, the 4 valence electron, sorry, the set of quantum numbers for these 2 electrons. Energy level 2, okay. Subshell P, so the L is gonna be 1. And here, 1 will be, MEL gonna be -1. Another one gonna be 0, right? But both is pointing up, so both are gonna be +1/2. Right, this is gonna be answer for this one here. Right, then 28. The value of the enthalpy change for the reaction below is 128.1 kilojoules. Then how many kilojoules of heat are consumed when 5.10 grams of carbon monoxide is formed as shown in the equation? So the first thing is to find how many moles of carbon monoxide you have here, right? So grams, each 1 mole of carbon monoxide, what's the molar mass? Carbon is 12 and oxygen is 16. So gonna be 28, right, grams of carbon monoxide. Okay, so here, 5.10 divided by 28. So 0.182 moles of carbon monoxide. So now let's convert the moles of carbon monoxide to find the kilojoules. How many kilojoules are formed? So I'm gonna do like this. Now let's go to the reaction. Oops. So here for each 1 mole of carbon monoxide, you have this amount of kilojoules, right? So then you can calculate it here. So what are gonna be our answer here in kilojoules, right? Please calculate them here. Okay, so I'm gonna stop this video here. I'm gonna record another one for the another questions.